Hello and welcome to the lecture of linear algebra. In this lecture we'll talk about the characteristic equation. So as I told you in the last lecture about the eigenvalues and eigenvectors, characteristic equation is one of the methods to find the eigenvalues of a matrix. So if A is a square matrix n by n matrix, you can find the value of eigenvalues using the characteristic equation. Say for example, A is 2, 3, 3 minus 6, right? And we know that all the values which satisfies, all the lambda values which satisfies this equation are actually the eigenvalues of this matrix A. Now in that case, A minus lambda I can be written as 2, 3, 3 minus 6 minus lambda 0, 0 and lambda. That comes out to be 2 minus lambda 3, 3 minus 6 minus lambda. Okay. Now, so if we have seen in the last lecture, this matrix could be invertible when its determinant is non-zero. Okay, so when its determinant is 0, right, so it means from here it can be determinant of 2 minus lambda 3, 3 minus 6 minus lambda, and should be equals to 0. Okay, so that remains the solution of this characteristic equation. So if we solve that, we know the determinant of this square matrix, which is 2 minus lambda minus 6 minus lambda minus 9, right? And that leads to minus 12 plus 6 lambda minus 2 lambda plus lambda square equals to 0. And if I solve it further, I can write it as lambda square plus 4 lambda and minus 21. Of course it's minus 9, 0, which can be factorized as lambda plus 7 and lambda minus 3. So it means the two eigenvalues can be lambda is equals to minus 7 and lambda equals to 3. So these two are the eigenvalues of the matrix A we just described. So we can use the eigenvalues to determine the invertibility of the matrix A also. So if let A is an n by n matrix, then A is invertible if and only if you have number 1, the number 0 is not an eigenvalue of A, and number 2 is that determinant of A is not 0. So as we seen here, from that example here, both these rules actually apply to this to matrix A. and A is invertible in this scenario. That means first of all the 0 is not the eigenvalue of this matrix A, and determinant of A is actually not 0, because you can see here this is determinant of A is actually minus 12, and minus 12 and minus 9 becomes minus 21. Okay. Now similarly we can find say for example, if this matrix is given to you, which is 5 minus 2 6 minus 1 0 3 minus 8 0 and 0 0 5 4 0 0 0 1, then we can find the eigenvalues as A minus lambda I, and you take the determinant of it, which is equals to comes out to be determinant of this thing here, 5 minus lambda minus 2 6 minus 1 0 3 minus lambda minus 8 0 0 0 5 minus lambda 4, and you have 0 0 0 as minus lambda. Now since it's a upper triangle matrix, and we know that for an upper triangle matrix the eigenvalues are nothing but the one that are on the diagonal, which means if I take the determinant here, it comes out to be 5 minus lambda whole square into 3 minus lambda into actually sorry, this is 1 minus lambda equals to 0. So we have a characteristic equation which can be written like that. So in that case we can expand this, and the eigenvalues here we know that is lambda is equals to 5, lambda is equals to 3, and lambda is equals to 1. But here, since the order of this lambda minus 5 is square, its multiplicity is 2, so you can write the eigenvalues 5 5 3 and 1. Okay, and similarly we can expand this to find the characteristic equation. If we expand this, we have the following result. Now we can easily see that the order of this characteristic equation is actually related to the dimension of this matrix A. So if A is in this is 4 by 4 matrix, here we have the maximum order of this characteristic equation polynomial as 4. So in general, if A is invertible, and it means this characteristic equation will have the same order as the dimension of the matrix A. Now since we already seen that, because it is 5 minus lambda whole square, so it comes at 2 times, because you can write this as 5 minus lambda and 5 minus lambda. So eigenvalue repeat itself, and this is called the algebraic multiplicity of this eigenvalue, and it's coming from the root of this characteristic equation. So in the proper way to write this the set of eigenvalues as 5 5 3 1, since 5 is repeating 2 times, so its algebraic multiplicity is 2. So we can reinforce that concept with another example, which is, let's say, lambda 6 minus 4 lambda cube minus 12 lambda 4 is equals so if this is a characteristic equation, we can write this as lambda 4 lambda squared minus so this is lambda 5, sorry, lambda minus lambda minus 12, and this comes out to be lambda 4 times lambda minus 6 and lambda plus 2, right? So here we have the eigenvalues as lambda is equals to 0, lambda is equals to 6, and lambda is equals to -2. Right. Now because 0 is into the power 4, it has a multiplicity 4. 6 has a multiplicity of 1, and similarly lambda is equals to -2 also has the multiplicity as 1. Okay. Another similar equivalent concept that is used in related to the eigenvalues and eigenvectors are what we call as similarity. This similarity property is used in various form of factorizations of a matrix. So let's understand what similarity is, then we'll see its application in diagonalization of certain matrix. So if we say that if A and B are n by n matrices, then we say A is similar to B. Now this is a different concept, that A is row equivalent to B or A is equals to B. This is somewhat different from those notions. In this thing we say A is similar to B if there exists an invertible matrix P such that P inverse A times P is equals to P, right? So that's what similarity condition dictates, that we say A is similar to B, that it is only possible if P inverse A times P is equals to P, right? So you can change the order here as well. You can write this as, if Q is inter matrix, which you can write as P inverse, this can be equally written as Q A times Q inverse equals to B, right? Or Q A B times equals to A, right? So you can actually change that order, and we can say B is similar to actually A. This is called what we call as a similarity transformation. Okay. It's called what we call the similarity transformation. So the important point here is that if from that property, that if A is similar to B, then they have the same characteristic, then A and B have the same characteristic polynomial, and their eigenvalues will be effectively the same with same multiplicities, right? So we write that as if A and B are n by n matrices, and they are similar, then they have the same characteristics polynomial, and hence the same eigenvalues, of course with same multiplicates. So we can easily prove that. I mean, if we know that B is equals to P inverse, if A is similar to B, it means B can be written as P inverse A times P, then B minus lambda I is nothing but equals to P inverse AP minus lambda I. And similarly you can write P inverse AP minus lambda into I can be written as nothing but P inverse into P, and we can take that P inverse out from here, which gives us P inverse AP minus lambda P, and which you can write this as P inverse A minus lambda I, and you can take the P out, so it means, which is nothing but, so the eigenvalues are the characteristic equation. If you take the determinant here, it becomes the characteristic equation. So B minus lambda I is nothing transforms to A minus lambda I. So it means if I take the determinant here, determinant of B minus lambda I, you can see here this is equal to determinant of P inverse A minus lambda I times P, and you know the property of determinant, that is determinant of A into B is nothing but equals to determinant of A into determinant of B, which is comes out to be determinant of P inverse into A minus lambda, determinant of A minus lambda I, and determinant of P, right? So all of them are being equated to 0 to find the solution for lambda. It means this and this one and this one will have no borrowing on determinant of A minus lambda I, right? So so we can actually use this property, and whenever A is similar to B and there is a P matrix exists which is itself invertible, such that B is equals to P inverse times AP, it means they will have the same eigenvalues and have the same multiplicity in their eigenvalues. Okay, now please remember that it is different from row equivalence or the equality condition. This is not same as row equivalent matrices or equal matrices. Now we can use that thing to eigenvalues, eigenvectors, to study the dynamical systems, the one we talked about in our earlier lectures about the difference equations or the Markov chains. And we can use the concept of eigenvalues and eigenvectors to solve those problems. And so to understand this thing, let's take example of this matrix A, which is 0.95, 0.03, 0.05 and 0.97. So what you have to do is to find the long-term behavior of this dynamical system, and such that it follows xk plus 1 is equals to a times x of k, as we have previously analyzed in terms of when we were dealing with Markov chains. So and we've been given initial starting point x0 as 0.6 and 0.4, right? So the first thing, in order to analyze that, so normally what we are accustomed to is we put on x0 in this equation, and then we solve for x1. Similarly, we put x1 that we just found and substitute it here on the right hand side to find x2, and recursively keep repeating that calculation to find the long-term behavior of this dynamical system. We can also use the eigenvalues and eigenvectors to end up with the same solution that we found out by using recursively. So how we can do that? Let's see that. So it means if A is the dynamical system, so the characteristic equation which governs this thing is 0.95 minus lambda, which is A minus lambda I, 0.03, 0.05, 0.97 minus lambda. Okay, so if we solve that equation, we will find out that 0.5 minus lambda into minus 0.7 minus lambda comes out as minus 0.03 times 0.05, and if you solve it in the form here, which is lambda square, comes out minus 1.2 lambda plus 0.92 equals to 0, right? So again, we can see here it's a square matrix, which is 2 by 2 matrix, and the polynomial order of the characteristic equation polynomial is actually 2. Now if we solve this equation, we can factorize it, If it's not factorizable, we can use solution of the quadratic formula, which comes out to be 1.92 plus minus 1.92 whole square minus 4 into 1.92 divided by 2, right? And when we solve for that, that comes out to be 1.92 plus minus 0.08 divided by 2. So lambda has two values, one is 2 and the one is 0.92. So we have two values for this matrix A that defines our dynamical system, or it defines our state transition matrix. In this case, it looks like that it is a probability transition matrix, because you can see here, as I told you earlier, that sum of the columns here should be equals 1, and so we can see here 0.95 plus 0.05 should be equals 1, and similarly 0.03 plus 0.97 comes out to 1 as well. Now given these eigenvalues, we can actually find the eigen vectors for these corresponding to these eigen values, and we know that how we can do that. We know that this is nothing but a. So if V is the vector, the solution for that one, so we say a v1 is lambda times v1, and a minus lambda times v1 equal to 0. So what we do here is lambda I, so I can subtract that, and let's say I say 0.5 minus 2, 0.03, 0.05 and 0.97 minus 2, and then I say v1 let's call this matrix v1 equal to 0. Okay, now I can find the solution here by simply saying as minus 1.05, 0.03, 0.05 and minus 1.03, and augment it with zeros, and once I can reduce that equation, I can find out the vectors v1 and v2. So we can see here simply that if you multiply by this certain factor, this can be removed, and when we do that, the answers comes out to be, I'm just writing it straight away, v1 as 3 and 5, right? Similarly for v2, you can write this as 0.95 minus 0.92, and then you have this as 0.03, and then you have 0.05, and similarly you say 0.97 minus 0.2 comes out to be 0.97 minus 0.92, and then you say v2 equals 0, and then you find this v2 as a solution. So we've already found that comes out to be 1 and minus 1. So the next step is actually we can write that x naught in terms of v1 and v2, because as we all told you that v1 and v2 are now the basis of this r square. Then x naught can be written as c1 times v1 plus c2 times v2, and which we can be written as v1 v2 and c1 c2, right? Because these two vectors v1 and v2 span r square, in which a is one of those matrices that contains possibly those vectors. So we can write that x naught c1 times v1 plus c2 times v2. So it means c1 and c2 can be found out simply by saying that this is v1 v2 inverse and into x naught. Now that inverse, that if you calculate here, is 3 5. So inverse of this thing here is this here, 3 5 1 and minus 1, and we know the x0 value is 0.6 and 0.40, and we can take that out by simply that inverse here. So what we do here is change the sign, minus 1 3, and switch the places, which is minus 5 and comes out minus 1, and which is 1 minus 1 by 8, and the determinant of this matrix, and this has 0.60 and 0.40. So this is the determinant of this matrix, this is the adjoint of this matrix, and this is x0. So it comes out to be 0.125 and 0.225. Similarly, this is your C1 and C2, and now we can easily find x1 as well. So we know x1 is nothing but equals to a times x0, and we have written as x0 as a times c1 v1 plus c2 v2. The answer becomes c1 times a times v1 plus c times a times v2. Now a times v1 is nothing but equals to v1, which is c times v1, and a times v2 is nothing but equals to so for the first eigenvalues, which is a times v1, is lambda times v1, which is corresponding value is 1, and similarly we have write this as c2 into 0.92 times v2, right? And similarly we can write x2 as a times x1, which is c times a v1 plus c2 times 0.92 times a v2, and this is equals to c1 v1 plus c2 0.92 whole square into v2. Now similarly we can write this as c1 plus c2 times 0.92 whole square v2, and if you keep substituting that, you will see that x of k can be written as c times v1 plus c2 times 0.9 to the power k times v2 for all possible values 0 1 2 and so on and so forth, right? So since we have already calculated the values of c1 and c2, I can write this c1 as 0.12535 and plus 0.225.92 to the power k, and v2 I know is 1 and minus 1, right? So this kind of solution we have already told you about in application to difference equations and application to Markov chains. So the long-term steady state behavior of this system is when k approaches infinity. When k approaches infinity, of course this term will approach towards 0, and you are left with the following steady state vector, right? So remember we talked about the steady state vectors, or the steady state probabilities, or the steady state of a dynamical system in our previous lectures. So when x approaches infinity, it means when the system have evolved a numerous number of times, effectively the system will have of the following state. Similarly, this is an example to illustrate what we have just learned today. So let's say if a is equals to 1 4 minus 4 and 2, you have to find the characteristic equation eigenvalue of a. So what we do is determinant of a minus lambda I, which is determinant of 1 minus lambda minus 4 4 2 minus lambda, and when we solve that, that becomes 1 minus lambda into 2 minus lambda and plus 16. When we solve it further, the answers comes out to be lambda square minus 3 lambda plus 18. Since it cannot be readily factorized, we use the quadratic formula, so it becomes minus b, which is 3, plus minus b square minus 4ac, which is minus 3 whole square, minus 4 into 18 divided by 2. So it comes out to be minus, actually 3 plus minus under root plus minus 9 minus 63 divided by 2. So you can see here the characteristic equation has no real solution. I mean, the values, the eigenvalues that we're getting from this one is actually complex values. So A matrix, this matrix A does not have any real eigenvalues. The matrix A, this matrix A is on the real space R square, and of course there is no non-zero vector in R square. This is non-zero vector in R square for which you can find AV is equals to lambda V. So this is a two-dimensional linear. These two vectors are linearly independent, and so they must span the space R square. And similarly, since we have no solution to this equation AV minus lambda V, because determinant is a complex so because the eigenvalues are complex values, so this resultant would be a complex lambda times V will be complex. So it means no vector in V will actually there is actually no non-zero vector in R square that can actually have a solution which is AV is equals to lambda V. In the next lecture we will talk about we will use a similarity of two matrices for diagonalization of a matrix. Thank you. Allah Hafiz.